case como nos got to see.
Are there any questions? All right, so what we have so far is that if we have something that will obey Hooke's law, that it will be in simple harmonic motion, which means we have a set of formulas that immediately will take place. That position is equal to some amplitude, cosine or sine, omega t plus phi. I'm going to go ahead and stick that on there. If you're using a LabQuest, you're going to have an additional piece out here because not everything's going to be centered around 0. V is equal to a omega, negative a omega sine omega t plus phi plus, that should disappear, and acceleration is negative a omega squared cosine, where omega is the square root of k over m, omega, which also equals 2 pi times what we generally call the frequency. And the period is 2 pi square root of k. Where k here is the spring constant or stiffness constant, constant of elasticity, something along those lines. I feel like there's some more equations that, and since the ideal spring exerts a conservative force, energy should be conserved. Since it's a conservative force, there's a potential energy formula. One half k delta x squared. And kinetic energy is the same as it always is. Now, what if we have something that is kind of like that? Let's take a look at the case of the simple pendulum. Bless you. All right, so what's going to make a simple pendulum? Again, we're not worrying about air resistance or any friction. No air resistance against anything here. No friction at the top. The mass is a point mass. In other words, we can approximate all the mass is concentrated at the end, and the string, this is ideal. It's not stretching, it's massless, the usual. All right, what are the forces acting? And it's just going to swing back and forth. It's not like we're dealing with centripetal motion where it's going in a circle. It's a pendulum. So what are the forces acting on that point mass? All right. Going up at that angle right there. Let's go ahead and make that theta. So that angle there is theta. Let's put our checklist for force diagrams. feeling pretty sure there's gotta be another force, because otherwise, if that's the only force, that mass, if I put it there, is gonna go accelerating towards the fulcrum. Yep. So now we can have some sort of balance. It won't be perfectly balanced. It is going to accelerate. All right, simple, so no friction. There's nothing elastic involved here. We do have tension. There's no other. It's not pushed against anything, and gravitational. All right. I know that as soon as I release it, it's going to move perpendicular to the string there. It's going to move in that direction. So it's going to move in that direction. So I'm going to go ahead and force the coordinate system here. It's going to accelerate. It actually accelerates in two different directions. What are the two directions of acceleration?
Down and to the right.
All right, that's one. You considering that too?
I would say no, it's still like one down and to the right.
There's one, it's accelerating in that direction, which I would consider the down and to the right.
Up and to the right.
Yeah, the other one is up and to the right. It is traveling in an arc here. So we have acceleration from the fact that the speed is changing, and we have acceleration from the fact that the direction is changing. The acceleration, because the direction changes, is called imagine there's a blank there to be filled in.
Okay.
Pardon?
No, I was gonna say kinetic, but like, no, that's not it.
No, it is not. So you are correct, it is not. Let's see how often I kick that now.
Centripetal.
Yes. So we have some centripetal acceleration and we have some tangential acceleration. So I would recommend that we break our coordinate system. Conveniently, they are perpendicular to each other. So break our coordinate system into the perpendicular and the central and the tangential axes. So do we have to break either of these up?
Wait.
Yeah. So let's break that up. See, there's the mass. The tension is up towards the center of curvature. This is some angle theta, and weight we need to break up. Weight is going this way. I need to break it up into perpendicular components. Well, this angle here is theta, so either that's theta or that's theta. We just have to figure out which one it is. Well, if that's theta, that's 90 degrees. This angle right here has got to be the complement of theta, which means that this angle down here is theta. So weight, we're breaking up into, oh wait, no, sorry, weight is down. Let's see if I can draw that again. So we have weight acting down, and we're breaking it up into components like that. That angle there is theta. My hypotenuse is weight. So what is this component that is perpendicular to the string? And what is it, the one that's parallel to the string?
Sine. Cosine.
So therefore, just like before, we're making the claim that I have tension acting this way, and I really should use F of T and not T over there. So if f of t going up towards the center at this angle theta here, and then I have a component of weight perpendicular to that, which is w sine of theta, and then opposite of that, w cosine theta. Making the usual claim that those two forces right there, it's the same as this. We've done the decomposition phase, we're now down to the equations of motion. We got two of them. What are the equations of motion?
Ft minus y cosine is equal to 0.
Not zero.
That's MA.
Be more specific.
MAC.
Yeah. That is the centripetal force, the tension minus W cosine theta is the centripetal force. It's mass equals mass times centripetal acceleration. All right, one down. What's the other one?
Weight sine theta is equal to MA.
Please recognize that these two A's are not the same. This is centripetal acceleration and this is tangential acceleration. There is one issue, or one thing that we at least have to acknowledge. We need to figure out the positive direction for the angle. Is theta positive or negative?
Positive.
All right, so theta is positive. So going this way is positive. What would be the direction of the acceleration?
But if you're going that way, theta was positive.
Wait, say that again?
If theta was positive, when we're going.
Well, we're defining it, so I'm fine with that being positive.
Whichever way would make it positive as being going to the right.
All right, so we have, one of the issues that we're facing here is the fact that I have an equation here with an angular component and a linear component. We need to somehow resolve that. We need to get them in terms of either both angular or both linear. I recommend both angular. Since acceleration is in that direction, if we think about it in terms of the angular acceleration, well, if it's going to accelerate that way, the angular acceleration is out. But theta, if that's, is in. In other words, if that's theta there, yeah, we can leave this as A, but recognize there's got to be a negative sign showing up somewhere. So let's get this all in terms of one style, mode, translational or rotational. What is the relationship between this A right here? This is tangential acceleration, which we just generally call acceleration. Between tangential acceleration and angular acceleration.
Would tangential have something to do with sine over cosine?
No, tangential, not tangent. Oh, tangential. Yeah, no, not a sine over cosine thing. Think about what is the relationship between linear speed and angular speed.
Let's change the letters.
Say it again?
The letters.
You said something about letters?
Yeah, you changed them.
Yeah, we need to do something more than that. There is a mathematical relationship. Natalie?
V equals R omega.
So what's the relationship between linear acceleration and angular acceleration? Someone take a shot at it.
You have to multiply omega by the radius to turn into a velocity
Or speed.
or speed.
Yeah, what about acceleration? I believe in you. You can do it. All right, let's derive it again. If V equals R omega, then delta V is equal to R delta omega. If something happens over a period of time,
R alpha. R alpha.
and over on the left-hand side,
A.
so this A over here, so this equation becomes, go ahead and do substitution, mg sine theta is equal to m r alpha. Mass cancels out. I'm left with g sine theta is equal to r alpha. Now, we need to deal with this negative sign. We could get away with this because that tangential acceleration could be a negative number. However, at this point, we have to come to some grips with that, and as we talked about before, if that's the positive angle theta, but alpha is in the other direction, a negative sign shows up somewhere. And so I put the negative sign in there, and now we have sine theta is equal to negative r over g alpha. And r is just the radius of curvature. In other words, it's the distance from our fulcrum to where the mass is. And let's go with a traditional, we'll just call that L for length. So this becomes negative L over G times alpha. Now all we have to do is solve that. And solving that is not particularly easy to do. So we have to rely upon the pre-computer days.
Why is it not over G, the whole thing?
Was it not over?
Why isn't it all over G?
Oh, in other words, have negative L alpha over G,
Yeah.
if you want to write it that way.
Or I guess, oh,
It's the same thing. Because L over G times alpha is L over G times alpha over 1, and then multiplying fractions, multiply the numerators, multiply the denominators. We talked about when we were deriving centripetal motion, however long ago. I introduced you, it was introduced, the small angle approximation. What is the small angle approximation?
If it was less than 1, then it was just considered 1. Or like slightly less than 1,
All right, so if what's less than 1?
something.
All right, so if something is actually much less than 1, we got part of it there.
Is it cosine and sine are each roughly equal to 1?
No, sine definitely wouldn't be. Cosine, you could make an argument for it.
approximately equal to theta, sine of theta, approximately tangent of theta.
So if theta is small, notice there are no units after the 1, so we're talking about radians here. So if theta is much less than 1, then sine of theta is approximately to the tangent of theta, which is approximately equal to theta. Cosine of theta is approximately equal to 1 minus theta squared over 2. If it's really tiny, you can just go with cosine theta is equal to 1, but it's a, if you say for small theta, cosine theta is roughly equal to 1, that does not hold up particularly well. So our equation that we had is sine of theta is equal to negative L over G alpha. So if we are dealing with a small initial angle, then we end up with theta being equal to negative L over G times alpha. If we look back over here at this equation, at Hooke's law, if the only force acting on the object is this elastic force, then this becomes MA equals negative K delta X.